Hi, my name is Adam Lekowitz. I'm a PhD student at UMass Amherst. Today I'll be talking about our paper on the online pause and resume problem. This is joint work with Nico Christensen, Jinheng Zhuo, and Adam Weirman at Caltech, Naman Bashir at MIT, and my advisors, Mohammed Haj Smiley and Prashant Shenoy. So I'll jump right in and talk about the motivation. Suppose that you have a cluster of some sort, and I give you an interruptible workload to run on that cluster. Your task is to run this workload while minimizing the resultant carbon emissions. We'll assume that the workload will take k units of time to complete, and the job needs to be finished at a deadline capital T, where T is greater than k. The electricity powering your cluster has a certain carbon intensity at each time step, meaning some amount of emissions per unit of energy. I've plotted an example here. This is a quantity that can be volatile as the electric grid changes throughout the day, and it's also an online quantity in the sense that you don't know what the carbon intensity will be in, say, 5 hours. Since we're minimizing our carbon footprint given T slots of time-varying carbon intensity, we're effectively trying to find the K lowest slots. We also consider a switching cost. In terms of carbon, this captures some energy overhead due to the extra time spent checkpointing or resuming the workload. So we'd like to design an algorithm that solves this problem in the online setting. We formalize a problem that we call online pause and resume. We say that a player must purchase K units of some asset. They want to minimize their purchasing and switching cost, and to preserve the deadline, we'll say that all of these transactions need to finish before T. If we knew the prices in advance, we could formulate an offline problem as follows. So C sub T here is the price, X sub T is our decision, and it's just binary. We run or we don't run. Here, beta is a coefficient that defines the switching overhead. We also have a constraint on the right-hand side that enforces completion of the job. We place some assumptions on the problem. So first we have this compulsory trade. Informally, if you have J slots remaining in your workload and there's exactly J slots left before the deadline, you must buy all of the remaining slots. Second, we assume that prices are bounded on this non-negative interval L comma U. Finally, to make the problem technically interesting, we assume that beta is not too large. Formally, it's less than U minus L over 2. We use competitive analysis, so if ALG represents an online algorithm's cost on a valid instance, and opt represents the offline optimal cost on the same instance, the competitive ratio is defined as this maximum ratio over all instances. Pause and resume has nice connections to broader tracks of work in online algorithms. In the realm of online search problems, pause and resume primarily adds the dimension of a switching cost. The most direct connection here is to k-search, and if we set the switching cost to 0, pause and resume is equivalent to k-search. On the other hand, pause and resume is also reminiscent of problems such as metrical task systems. Compared to these problems, pause and resume adds a long-term constraint, this dynamic where a certain amount of capacity must be met before some deadline. To our knowledge, pause and resume is the first problem to integrate all three of these characteristics into a single problem, which prompts questions about the best way to approach it. The approach we adopt takes inspiration from an existing threshold-based algorithm for k-search. This algorithm uses k decreasing threshold values based on L and U. As prices arrive online, whenever the price is less than the current threshold value, the algorithm purchases and moves to the next threshold. So our idea is to generalize this algorithm for pause and resume, but the most natural question is, how do we deal with the switching cost? We leverage the intuition of hysteresis or resistance to change. So we're going to define two families of low and high threshold values and switch between them based on the current state. The intuition is as follows. Consider we have thresholds like this where we have an upper and a lower threshold. If x sub t minus 1 is 0, we know that we didn't purchase at the previous price. This means that if we do accept the next one, we'll have to pay switching cost. So intuitively, the price that we should be willing to accept should be better to offset that extra cost. Conversely, if x sub t minus 1 is 1, we know that we did purchase at the previous price. So if we choose to stop purchasing, we're going to have to pay beta to checkpoint everything, and we should be willing to accept a slightly higher price if it reduces the switching. So we call this algorithm DTPR, which stands for double threshold pause and resume. DTPR is alpha competitive, where alpha is the solution to this equation. Order-wise, alpha is sublinear in U over L with an additional linear dependence on beta. We show that alpha is the optimal worst-case competitive ratio for any deterministic algorithm by constructing a special class of hard instances where any algorithm and action, what any action an algorithm makes leads to a competitive ratio of alpha or something worse. In summary, we introduce and study this online pause and resume problem with the motivation of modeling carbon-aware problems and problems in sustainability. This is the first online problem that features all of these characteristics of time-varying costs, switching costs, and long-term constraints. We give a double threshold algorithm to solve this problem and show it achieves the best competitive ratio. In the full paper, we also implement our algorithm for the motivating application of carbon-aware load shifting and show it performs well on real data.